Alright, I'm going to try to be a little bit more high-tech with this last video today because we're going to use the graphing calculators a lot. We're going to talk about more exponential and log models. I'm going to take you through one of the examples that's in the book. So if you did bring your book home, just take a look at this problem on page 262. This is example number 5. If you didn't bring your book home, you'll need to write this down, but I've pretty much just taken it as it is in the book there. It says, on a campus of 5,000 students, one student returns from vacation with a virus, and the spread of that virus is modeled by this function when t is greater than or equal to 0. So you can see that is kind of a combination of a rational function, because we've got a fraction with a variable in it, and an exponential function. We've got that e to the negative 0.8t down in the denominator. It says y is the total number of students infected after t days. It says the college will cancel classes when 40% or more of the students are infected. So we're going to do all of this with the calculator. So the first thing I would recommend is going ahead and trying to graph that function in your calculator. And I've done that on my calculator as well. So you may want to pause here for a second if you need to look at that equation and get it into your calculator, because I'm going to go to my calculator now. And see if I can zoom out so you can see this whole graph, this whole function in our calculator. It's a little bit of a glare there. You can see, make sure you get that negative 0.8x in parentheses in the denominator. And if you graph this on a standard window, you can see the beginning of the graph. At least it looks like an exponential function, and that's going to be the case at the beginning. Although this graph will end up leveling off later on. If you've done anything in AP Biology with carrying capacity, this is what we call a logistic growth curve, and it's going to kind of flatten out as we get toward the end. But that's what that should look like in your standard window. All right, and then we're going to talk about what happens in this problem. It says, first, how many students are infected after 5 days? So we need to know after 5 days what's happening. So we can just use our table of values if we want, or we can go right on our graph and calculate a value when x equals or when t equals 5. Type that in there, you get 54.019. So since we're talking about a number of students, we would round that and we would say that 54 students would be infected after 5 days. Then part B says, after how many days will the college cancel classes? Well, it says we're going to cancel classes if we get 40% or more of the students that are infected. So we have to figure out 40% of the 5,000 students. So 0.4 times 5,000 is going to give you 2,000. So we need to figure out in this equation, in this function, what value of t will make the value of y, the total number of students, greater than 2,000. So going back to my graph, and now the book will solve this by hand. There's really no reason we're ever going to have to solve something like this by hand. So we're just going to graph this function against y equals 2,000. Obviously our standard window is not going to work for us there, because in our standard window y max is 10 and we need y to be at least 2,000. So I'm going to go change my window. I'm going to make my y max something bigger than 2,000. So I'll go like, say, 2,500. And we'll see what that does for us. There's our curve again, and y equals 2,000. Notice we don't quite see the intersection here yet. So we're going to need to extend our x's a little bit more. So back to my window. My x's are going up to 10 right now. Let's see if I go up to 20, if that'll be enough. So now, there we go. I can see now that this curve is going to intersect y equals 2,000 somewhere on our screen here, and then we'll have the calculator tell us where that is by finding the intersection of those two things. So I'm going to calculate the intersection of this curve with y equals 2,000. My guess, just get somewhat close to it there. And the calculator gives me x equals 10.139, and that's the number of days. So after a little bit more than 10 days, we're going to have 2,000 students that are infected with this virus, and therefore we're going to cancel classes. All right, since I've got a little bit of time left here on my video, I'd like you to see what that entire graph looks like, because it right now looks like an exponential growth curve, but over time, if you end up with half of the students, almost 40% of the students infected, at some point the rate of that infection is going to have to slow down because you're simply running out of students that will be infected by it. So see if I can expand this graph a little bit more. And so obviously the most students that could be infected is 5,000. So that's all we've got. So if you go a little bit more than 5,000, go to 5,500. And now you can start to see on this graph that there's a place where this graph starts to level off. There's a place where the graph almost kind of looks like it turns inside out, and the rate of increase is getting smaller. We're still getting more students that are infected, but not at quite a rate. And at y equals 5,000 up there, you can see where the graph goes horizontal a little bit, or nearly horizontal. That's because we're approaching that maximum number of students that can be infected. Again, for you bio people, that's your carrying capacity if you're talking about ecology. So I just wanted you to see that, because it's not your standard exponential growth model. It is for a while, but then we reach some kind of tipping point there in between where that function's still increasing, but not as quickly as it did before. All right, so that's one example of using the calculator to solve an exponential model, and we will do some practice problems with the calculator in class tomorrow.